I'd like to spend this video talking about how great the last video was. What we did in the last video was part B of example 2. And I want to point out, using this video, how much faster it is to do this method than any other method. So the original way we learned how to create a Taylor polynomial for a function is by taking repeated derivatives. So let's give that a try with this same function, 1 over 1 minus x. Again, we already know what the polynomial expansion of this is. We just did that in the last video. So I'm not going to talk about that again, but let's just see what the process is here. So if we start off with f of x equals 1 over 1 minus x, the first thing I need to do is take a whole bunch of derivatives. So I'm going to find f prime of x, and you can use quotient rule here. I wouldn't, because this can be easily rewritten as a power of 1 minus x raised to the negative 1. And then if you write it as a power, then it's a simple power rule process. So bring the negative 1 out front, drop the exponent down by 1, so that negative 1 goes down to a negative 2. But don't forget the chain rule, right? So we multiply by the derivative of 1 minus x, which is negative 1. So this is negative 1 times negative 1 is positive 1 times 1 minus x to the negative 2. All right, and we'll keep on going. We'll take the second derivative. Negative 2 times 1 is negative 2. This is just another power rule problem. The negative 2 drops down to a negative 3, but we remember the chain rule, and then it's the same negative 1. So negative 2 times negative 1 is positive 2, and we have 1 minus x raised to the negative 3. Keeping on with this pattern, we find the third derivative by taking the derivative of the second derivative. 2 times negative 3 is negative 6. Our negative 3 drops to a negative 4. We still have that negative 1 for the chain rule, so this is going to be 6 times 1 minus x to the negative 4. Let's do 1 for good measure. One more for good measure. The fourth derivative of x is going to be the derivative of the third derivative. That's negative 4 times 6 is negative 24. And then we drop the exponent down by 1, and we remember the chain rule, and we get negative times negative is once again positive. Positive 24 times 1 minus x raised to the negative 5. And we're going to continue this pattern forever. Okay, the next step is realizing that we're centering this at c equals 0. So we're going to evaluate f of 0. We're going to evaluate f prime of 0. We're going to evaluate f double prime of 0. All of these evaluated at 0. And until we can find a pattern. So we have, evaluating this at 0, we have 1 minus 0 raised to the negative 1. So that's 1. Notice that we always have 1 minus 0 raised to a power. 1 raised to any power is going to be 1. So all of these right here in the parentheses, those are all just going to turn into a 1. So all we have are the coefficients of 1 and 2 and 6 and 24. And there's some pattern here that perhaps you notice. If you don't notice it, you'll probably notice it soon enough. All right, the next step is that we are going to take these coefficients and we're going to create our Taylor polynomial series by taking the first term. That's our degree 0 coefficient. This is going to be our degree 1 coefficient, so 1x. This is going to be our degree 2 coefficient, so that's going to be 2x squared. Notice I'm putting it way up here because we have to start dividing by the factorials. This is going to be divided by 2 factorial, right? We could have said divided by 1 factorial on this one. We could have said divided by 0 factorial on this one, but since 0 factorial and 1 factorial are just 1, we don't worry about them. So we'll keep on going. We've got 6 as our coefficient for our degree 3, and since it's degree 3, we're going to divide by 3 factorial. 24 is our coefficient for degree 4, so we put 24 times x to the 4th. Degree 4 means we divide by 4 factorial, and that's a pattern that continues on and on and on. So you probably have noticed that we have some things that can cancel. For example, 2 factorial is the same thing as 2. So we're going to get just plain old x squared. And 3 factorial is the same thing as 6. So we're just going to get plain old x cubed. And 4 factorial is the same thing as 24. So we're going to get x to the fourth. And you might say, well, why is this happening? Well, it's because of how the power rule works, right? We're multiplying 4 factorial times 5, right? -1 for the chain rule and the -5. So it's +5 times 4 factorial is going to give us 5 factorial. And then we'll get a 6 times our 5 factorial to get 6 factorial. So every single time we take another derivative, these values are going to get multiplied by the next integer, and that's exactly what the factorial function does. Oh, wait, hold on. 1 plus x squared plus x cubed plus x to the fourth. That's exactly what we already knew was going to happen. And this is going to be what we already knew the answer to be, which is the sum from n equals 0 to infinity of x raised to the n. Okay? I'm not going to bother finding the interval of convergence because we've done that in the past. We already know how that works with the ratio test, but we also know that we already have the interval of convergence from a much faster method than the ratio test. So that's fairly convenient. All right, so that's part A. So we know how to do this using the Taylor polynomial generation. Now, this is kind of a nifty little extra thing we could do. We normally don't, but long division can actually be used to create these series. How? Well, I'm glad you asked. Remember that fractions are just division. So let's try to draw that arrow again. There we go. We're going to divide 1 by 1 minus x. So can I get a horizontal scroll? Yeah, I can. All right. So I'm going to take 1 divided by 1 minus x, which I can rewrite as dividing 1 minus x into 1. Now that seems backwards, right? Because we've got our degree 0 first and our degree 1 second, but we're kind of used to seeing our degrees grow in this section, right? So 1 times what gives us 1? Of course, that's 1. So I'm going to multiply 1 times 1 minus x. I'm going to subtract. I've got 0 x's to subtract a -1x from. Well, 0 minus -1 is 1. So then I say, let's see, I'm going to put something here so that when I multiply it by 1, I get x. Well, that's, of course, got to be x. So x times 1 minus x is going to be x minus x squared. All right, well, I've got 0x squared that I'm going to subtract -x squared from. And if you do 0 minus -1, I think we just did 0 minus -1. We got 1. We're still going to get 1. So we're seeing a pattern here, right? So we have to say what times 1 will give us x squared. Well, of course, that's going to be x squared. And when we take x squared times 1, we get x squared. X squared times -x, we get -x cubed. So we're going to subtract this guy. But we don't have any x cubes to subtract it from. So we have 0 minus -1. Oh, still 1. All right. I haven't mentioned, but these guys go away, right? The x squared minus x squared, the x minus x, the 1 minus 1. Of course that happens because that's how division works. We have to get all of the stuff from the first column before we can move on to the next column. So anyway, it's pretty easy to see that this is going to create the exact same infinite series that we talked about before. It's very similar to when you're dividing numbers. Like if I divide 1 divided by 3, and I put a 3 out here and a 1 inside here, I just keep on putting 0.00000 and expanding that out as far as I can until I find a pattern. This is the same deal. So this is yet another way that we can use to generate our Taylor series.